We build machine learning systems to eliminate human error. We design them for perfect mathematical objectivity, expecting clean, rational outputs. Yet, when applied to complex human realities, these optimized architectures consistently produce discriminatory outcomes. An algorithmic health risk score systematically underestimated the medical needs of Black patients. Credit scoring models actively disadvantaged Hispanic borrowers with identical financial profiles to their white counterparts. Risk assessment algorithms in the criminal justice system disproportionately flagged minority defendants as high risk. To understand how this happens, we must look at the formal mathematical definition of algorithmic bias. Bias exists in a learning system when a specific, measurable disparity occurs. The equation breaks down like this. A chosen fairness metric, represented by f, demonstrates a non-zero disparity between the algorithm's predicted outcomes, y hat, and the ground truth reality, y. The final variable, a, represents the protected attribute. This is where the math intersects with sociology, isolating vulnerabilities based on categories like race, gender, caste, or dialect. A non-zero result here means the system is biased. But this bias is rarely a monolithic coding error or a malicious function. It is a compounding phenomenon that infiltrates the architecture through multiple, distinct vectors. Researchers divide these vectors into 4 mathematically and sociologically distinct families: historical or representational bias, selection bias, algorithmic bias, and emergent feedback bias. These vectors gestate and compound within the standard machine learning pipeline. To build an equitable AI system, developers must trace these specific vectors and impose hard mathematical constraints at 3 exact stages of development: pre-processing, in-processing, and post-processing. Unless we dissect the entire machine learning life cycle, attempts to de-bias an algorithm are cosmetic fixes that leave the underlying architecture of systemic harm intact. The life cycle begins at data curation and ingestion. This is where the raw material is gathered to train the model. It is also where historical or representational bias enters the pipeline. AI models absorb the structural inequities hidden within historical datasets and translate those unequal social power relations into mathematical rules. In 2018, Amazon developed an AI-powered hiring tool to automate resume screening. The developers trained the model on a 10-year dataset of past hiring decisions from an industry that was overwhelmingly male-dominated. The mathematical consequence was severe. The algorithm identified a pattern in the historical data and began assigning negative statistical weights to female-associated terms. A resume mentioning a women's chess club was actively penalized, regardless of the candidate's actual qualifications. This data layer is also vulnerable to selection and measurement bias. This occurs when marginalized groups are systematically omitted or mislabeled during initial data collection, such as facial recognition algorithms trained primarily on images of lighter-skinned individuals, resulting in high error rates for darker-skinned faces. Correcting these skewed representations requires aggressive pre-processing interventions. The data must be calibrated before the model ever begins to train. One specific intervention is dataset reweighting. Engineers artificially assign higher mathematical influence to training samples from underrepresented groups, forcing the model to value their data proportionally. This is often paired with data augmentation, which synthetically increases the diversity of the dataset to balance demographic representation and neutralize disparities early. Raw data serves as a mathematical artifact of historical power dynamics. Left uncalibrated, these imbalances are encoded into the model's internal logic, where they persist as invisible drivers of future predictions. Once the data is preprocessed, the model moves to the training stage, where it begins actively learning how to make decisions. This stage operates on the principle of empirical risk minimization. Algorithms are designed to seek the absolute lowest error rate possible, optimizing for global accuracy across the entire dataset at all costs. This creates a structural algorithmic bias. When a system prioritizes global accuracy, it inherently sacrifices performance on minority classes. The algorithm achieves its goal by treating severe demographic disparities as acceptable statistical noise. To counter this, engineers must inject formal fairness constraints directly into the loss function during in-processing, forcing the algorithm to balance accuracy with equity. There are two mathematical definitions of group fairness. First, demographic parity. This constraint dictates an AI model must assign identical probabilities of favorable outcomes across all protected populations. The selection rate must be equal, regardless of input distribution. The second is equalized odds. Instead of demanding equal selection rates, this constraint requires the AI system to produce mathematically similar false positive and false negative error rates across different demographic groups. These constraints are enforced through techniques like adversarial debiasing, where the model is dynamically penalized during training if its outcomes begin to favor a specific demographic. In this framework, fairness is treated as a rigid mathematical constraint, hard-coded directly into the optimization architecture to ensure equitable outcomes are prioritized alongside accuracy. We reach the output stage of the pipeline, where the trained model begins rendering individual predictions. Here we encounter the black box problem. Deep learning networks reach conclusions through millions of opaque parameter interactions. Their internal logic defies simple human interpretation. This opacity directly violates the fate principles: fairness, accountability, transparency, and explainability, which are mandatory for deploying analytics in high-stakes business environments. To audit this logic, data scientists rely on explainable AI, or XAI. It acts as a mandatory post-processing diagnostic tool to tear open the black box. One primary XAI technique is LIME, Local Interpretable Model Agnostic Explanations. LIME approximates model behavior in local decision regions. It maps exactly which variables influenced a specific outcome, justifying, for example, why a single individual's loan application was rejected. By contrast, Shapley Additive Explanations provides a global view. It calculates and assigns feature importance scores across the entire system, showing administrators which variables carry the most weight in the aggregate. These XAI diagnostics reveal exactly where a model is skewing. Engineers use these insights to apply calibration-based fairness corrections, adjusting prediction thresholds to equalize error rates right before the final output is finalized. Fostering accountability in high-stakes environments necessitates a verifiable audit trail. Interpretability provides the mathematical proof required to justify an algorithm's decision and ensure it remains aligned with established ethical standards. The mathematically optimized model is finally deployed into the unpredictable real world. This initiates the fourth and final threat, emergent feedback bias, occurring when an algorithm's output alters the real-world environment, generating skewed conditions for future inputs. The Compass criminal risk assessment algorithm demonstrates the severity of this cycle. Because of historical data, Compass disproportionately flagged specific minority neighborhoods as high risk. Law enforcement utilized those predictions to direct disproportionate policing to those communities. Increased police presence inflated local arrest rates. Those higher arrest rates were then fed back into the algorithm as new data, mathematically justifying the initial biased prediction. In dynamical systems, this self-reinforcing cascade is an increasing spectral radius. The system's instability and bias grow exponentially over time with every feedback cycle. Isolated statistical fixes applied in a sterile development environment are entirely insufficient to stop emergent bias once a model goes live. This diagram illustrates an AI governance model, showing why technical fairness metrics must be enveloped by socio-technical frameworks. Regulatory imperatives like the EU AI Act now mandate continuous monitoring for high-risk applications, imposing strict penalties for non-compliance. The final operational safeguard in these frameworks is the human-in-the-loop system. Automated recommendations in high-stakes environments are structurally required to pass human expert review before execution, ensuring contextual judgment intercepts runaway algorithmic feedback. Achieving equity in artificial intelligence requires abandoning the illusion of a purely mathematical fix. It demands a life-cycle-wide commitment to algorithmic accountability, bridging the gap between statistical optimization and rigorous human oversight.